All right, so today is going to be like entirely review from Science 10, okay, V equals D over T stuff. All right, so what we're going to review here are scalar versus vector quantities, okay, difference between like velocity and speed, distance and displacement, okay, the two different V equals D over T formulas, how they work, okay, stuff like that. So hopefully it's all going to seem familiar to you from there. So key points, and anytime guys I'm doing a lecture, okay, there'll be a lesson number and a title, and then there'll be key points. Those are the things that could end up, like let's say on a quiz, okay, on a Tuesday or a Thursday, that kind of stuff. So understand that the motion of objects and systems can be described in terms of displacement, time, and velocity. That would be V equals D over T, or V equals D over T. No, I didn't just stutter. Okay, those are two different formulas. Okay, this one has to do with the scalar quantities, speed, distance, and time. Okay, and this one has to do with the vector quantities, velocity, displacement. Okay, so important for us to remember that there are differences there and how we treat them as different. Okay, define operationally, compare and contrast, okay, those things, and then obviously define velocity as a change in position during a time interval. What that means is something you learned in Science 10, and that is that this formula can be expanded out to look like this. Final position minus initial position divided by time, because displacement is your change in position over time. Okay? All right, is that ringing a bell? All right, something we learned back in Science 10 is that the way we describe how and, well, let's say, how we get from one place to another, okay, or how far it is from one place to another is totally messed up, okay? Because if I were to ask you, unless of course you're in my Science 10 class in which you already know the correct answer, okay, but if I were to ask you, how far is it to Edmonton? Okay, most of you would say around 3 hours, 4 hours, right? What do hours measure? Time. Did I ask how long it takes to get to Edmonton, or did I ask how far Edmonton was? I asked how far. But like as a societal norm, that's what we do. If someone asks you how far away something is, you tell them how long it takes to get there. It's just what we do. Okay? And that's honestly what most people expect when they ask you that question. Okay? I mean, think about all the time someone has asked you about, you know, how far something is and how many times you've told them how long it takes. Okay? It's just something we do. Right? Societally, that's how we describe how far things are. The problem is that how far things are is a number that doesn't really change. How long it takes to do that does. Okay? How far apart they are just depends on their two positions. Okay? If we're talking about Okotoks and Edmonton, those things aren't changing their position. They are fixed. Okay? How far apart they are does not change. But how long it takes to get to Edmonton can change drastically. Okay? I've gotten there in less than 3 hours. I wasn't driving. Okay? My crazy friend was. Right? But yeah, you can do it. Okay? You can go really stupidly fast and don't stop. Okay? Or it can take as long as 9 hours. Because you get in a snowstorm and you got to drive, 35 kilometers an hour, and it can take a really long time to get home. Okay? So telling people how long it takes is not necessarily always going to be correct. Okay? It's what's convenient, it's what we do, but it's not technically how far. Okay? That's something we have to be mindful of in physics, because if a question asks you, how far is it from here to there, don't tell me how long it takes. That's not what I want. Okay? The question wants how far, it wants a distance. Okay? So it's just something we have to kind of get our heads around a little bit. Okay? So if I was, let's say, describing, I want to get from, Okotoks to, I don't know, Janet out here by Chestermere. Are there a number of different ways I could go? There are, and each of them would take a different amount of time, and each of them would be a different distance. Okay, so sometimes we also have to specify that. All right, so if someone asks me, or if I tell someone Calgary's 40 kilometers away, is that like a terribly accurate or useful description? And it isn't, but it also doesn't have to be. We have this vast system of roads that we can follow that have generally decent signage, okay, that we could follow in order to get there. And by the time we got there, we would have driven about 40 kilometers, okay? But if I'm in a roadless, trackless environment, and I say it's 40 kilometers away, is that very useful? Yeah, it's not useful at all, okay? How many choices do I have for what direction to go? 360. What are my chances of getting to the right place? 1 in 360. That's pretty slim. Okay, and I don't want those kind of odds. Okay, so in certain cases, telling someone something's 40 kilometers away is perfectly adequate. In other cases, it's worse than useless. Okay, and probably get them horribly lost. So we have to be mindful of that. Okay, and again, we have to be mindful of telling people the right units. Okay, I'll give you an example of when the giving time instead of distance thing screwed me over big time. Okay, me and a buddy of mine were doing a backpacking trip through Kootenai National Park, and we had it was our longest day. It was like 38 kilometers, 2 mountain passes, and it was like 6 o'clock in the afternoon, and we weren't where we were supposed to be yet, and we really thought like we should have been. We're old, but we're not that slow. And so we sat down and we were looking at the map. We're out of water because all the streams are dry. We can't filter. And don't really, we've eaten snacks, but we're kind of getting low blood sugar. And it's not making sense to us. We feel like we're lost. And all of a sudden, this guy comes running up the trail towards us, running uphill towards us. And dude, stop for a second. He stops and like, hey, do you know where Tumbling Creek Campground is? And the guy looks at us like, oh yeah, mate, it's 20 minutes down the trail there. And we're like, oh, sweet. Okay, so we were really close, we're not crazy. Okay, it's 20 minutes. He bops off, okay, just takes off and he runs some more with this gigantic pack, okay? And us two out-of-shape teachers on their summer vacation stumble downhill towards this campground, and an hour later arrive there, and we are like, we're gonna hunt that guy down. That guy lied to us, man. Like you said, 20 minutes, it's an hour. It's not making any sense. Then we have some dinner and we have some water. I think about like, turn to my buddy, who's also a physics teacher. And I said, Sean, do you know what we just did? He looks at me and goes, we let somebody tell us how far away something was in time and not distance. And I'm like, yeah. He looks at me and goes, we will never speak of this again. I tell a story every semester. Yeah, it's not a proud moment, but it's one of those examples of that didn't work. Why didn't it work? This guy was probably like SAS Special Forces guy doing a training run with his 100-pound pack. Okay, he was in way better shape than us. He was running uphill. We're two out-of-shape teachers on the summer vacation walking downhill. Of course, it's going to take us 3 times as long as him. Okay, it's the same distance, but we're not running. We're stumbling. Okay. So those kind of situations are things where, again, we got to be mindful that the way we describe things in normal life is not good for being physically accurate. Okay, so we could also, instead of saying Calgary's 40 kilometers from here, we could say Calgary's 40 kilometers away on a vector of 13 degrees west of north. Okay, so if we were down here in Okotoks. Okay, so if we're down here in Okotoks, okay, and we want to go to Calgary, yeah, okay, in a straight line, okay, this would be due north. That would be about 13 degrees west of north. If I had a helicopter, I could fly right along that line, okay, and I would get right into downtown Calgary from here, okay. Does that make it better than the previous description? It doesn't make it necessarily better. It's different, okay? In a certain situation, it might be more or less useful, okay? But that's what we got. Okay, so what I'm saying here is that a scalar value, a scalar description of something isn't necessarily better or worse than a vector description of the same thing. Okay, some have certain uses, some have certain uses. Okay, they're equally valid. Is there one that's more accurate? Would a vector description be more accurate than a scalar description, or vice versa? Okay, we almost always get the answer yes. Yeah, vector would totally be more accurate. But it actually isn't more accurate. In fact, a vector description can be less accurate. It's more descriptive. It gives you more information, but it's not necessarily more accurate. Okay? I'll give you an example. Okay, so those are the two numbers we were talking about just a minute ago. Which one of those is more accurate? 40.00 or 40? 40.00. Okay, accuracy is about how you measure it, not about what you measure. Okay, both of these measure how far. Okay? But this one is accurate to the nearest 10, plus or minus 10 meters. This is accurate to plus or minus 1,000 meters. Okay? There's no numbers past the one's position in that number. Okay? It's accurate to plus or minus 1 kilometer, 1,000 meters. The other one is accurate to plus or minus 10 meters. So basically, these two things were measured with two different sticks. Okay? One stick is a kilometer long, and I used it 40 times. Okay? The other one was measured with a stick, okay, that is 10 meters long. Okay? Am I going to be more accurate with that one? I'm going to get more measurements with the shorter unit. Okay? So accuracy depends on how you measure, not what you measure. Okay? So it's possible for a vector description, like this number, to be less accurate than a scalar description. Okay? All right, so with vectors, okay? Obviously vectors in like science 10 were like north and south, right and left, positive and negative, and that was the extent of it. Okay? In physics 20, we're going to bring in the trigonometry. Okay? So we'll start dealing with compass directions like 13 degrees west of north. Okay? So there would be a westerly component, a northerly component that would make the triangle up. Okay? And that's where the trigonometry part will come in. Okay, now, if you did Science 10, you probably had an example similar to this one here. Okay? If we're describing a trip from someone's house to Walmart. Okay? And you're going to say they're going to walk. Okay? Now, unless you live like right behind Walmart, you cannot walk in a straight line from your house to Walmart. Agreed? Okay? Unless you can pass through walls and trees and things like that. You can't walk in a straight line. So let's say that from my house, I get on the sidewalk and I start walking, okay? And I follow this line here. I go across the river and follow the road and take some turns, and eventually I end up at Walmart. Okay? Let's say that in walking that path, I walk 4 kilometers. Okay? Is that a distance or a displacement? Spoiler alert, the answer is on the screen. It's distance. It's how far I had to walk in order to get there. Is it how far Walmart is from my house? In a straight line, Walmart's closer than that, right? I just couldn't walk in a straight line. I had to travel 4 kilometers to get there. Okay? If I had a helicopter, I wouldn't shop at Walmart because I'd be rich. But okay, let's say I was able to go in a straight line because I had a helicopter. Okay? Is that going to be shorter? Right? Shortest route between 2 points is always a straight line. So that's going to be shorter. This will be my displacement because it's how much and in what direction I change my position. It's not about how far I go. It's about how much I change my position. Okay? And it's a vector quantity. So let's say that for that one, we'd be looking at 2.8 kilometers, okay, at, what are we looking at there? 40, let's see. Degrees north of west. Okay? If it takes me a half an hour to walk to Walmart, what's my speed? So I walked 4 kilometers in half an hour. What's my speed? 8 kilometers an hour. Okay? How do we do that? Over t. Okay. I know the distance I traveled was 4 kilometers. I know the time it took me was 0.5 hours. Okay, 4 divided by 0.5 is 8 kilometers per hour. Okay, what's my velocity? Same number or different number? Remember, velocity is vector. It's displacement divided by time. Okay? So I only changed my position in a half an hour by 2.8 kilometers at 40 degrees north of west. Okay? Divided by 0.5 hours. Well, that's going to give me 5.6 kilometers per hour at 40 degrees north of west. Okay? Velocity tells me how quickly and in what direction I change my position, whereas distance tells me how fast I'm going. Period. Okay. If you get pulled over by the police, which one do you want to tell them when they ask you how fast you're going? Your speed. Okay? If you tell them your velocity, you'll probably be subjected to a sobriety test. Okay? Because they'll sound really weird. You know how fast you're going? Yes, officer, 111 kilometers per hour at 30 degrees south of west. How much have you had to drink today, sir? Okay? That's not the answer they're expecting. They want a scalar value. They want to know how fast you're going. That's speed. Okay? If they ask how fast and in what direction are you going, then the other answer would be appropriate. Okay? In most cases it wouldn't be. Okay. All right, so now I've walked to Walmart. I'm old, so I forget things. Get to Walmart and I've forgot my phone and wallet. I have no way to buy anything. I'm not going to walk around Walmart for the fun of it. So I turn around and walk exactly the same path home. Half an hour later, I'm back home. How far have I walked? 8 kilometers in total. Okay. What's my displacement? 0. Okay. Remember, displacement measures your change in position. My starting position was home. My ending position is also home. I haven't changed my position if I come back to where I started. Okay? Therefore, my displacement will be 0. What would my speed be? Still 8 kilometers per hour. Okay? I walked home along exactly the same route. It took me exactly the same amount of time. I've gone 8 kilometers in 1 hour. My speed is still 8 kilometers per hour. What's my velocity? What did we just say? If I end up back at home, my displacement is? What's 0 divided by anything? Right? What's my velocity? 0. Okay? Because technically, or from a vector perspective, I have accomplished nothing. Okay? I ended up back where I started. Therefore, I haven't changed my position, so there's no way for me to express the rate at which I changed my position, because I didn't. I ended up back where I started. Okay? This is why the odometer in your car, the one that tells you how many kilometers it's been driven, measures distance. Okay? If it measured displacement, what would it read when you get home? No. It'll read how far it is from the dealer you bought it at to your house. You go back to the dealer, it'll read 0. Okay? That's a trick question. Okay? Your odometer, you didn't get your car unless it was delivered to you at your house. Okay, you got it at the dealer and then drove it home. Every time you go back to the dealer, it'll read 0. Okay? That's why that doesn't work. It would be perfect when you want to trade it in. Okay? Drive back to the dealer and go, it's brand new. See, it's got 0 kilometers on it. That's silly. Okay? That doesn't give an accurate representation of anything. Okay? That's why it reads distance. All right? Everybody all right with that idea? So sometimes scalar is good, sometimes vector is good. Okay, in this situation, let's say you're hiking, okay, in, well, this is Jasper National Park. Let's say I start here at Seldom Inn Campground, and I want to walk to Snake Indian Falls Campground. There's a sign just outside of Seldom Inn Campground. Does it give me distance or displacement to the next campground? What do signs on the roads here give you? Distance. Okay? Because what do they assume you're going to do? Follow the road. Or in this case, follow the path. Right? If that sign said, the sign actually says Snake Indian Falls 32 kilometers, okay, it goes along here. Okay? It assumes I'm going to follow the trail like a sane person. Okay? If it said Snake Indian Falls 19 kilometers, okay, at 35 degrees west of north, that would assume I'm going to do that. That would be difficult. Okay, this gray stuff, that's a glacier. There's a big mountain here. There's all these rivers that would have deep canyons and no bridges. Okay, it assumes I'm going to follow the path because that's the easiest way to go. Okay, in that case, again, giving me the scalar description is more appropriate, okay, than giving me the vector description. Okay, if I'm in the search and rescue helicopter, I want this one. I want the vector one because I can go in a straight line wherever I want. Okay, but if I'm going along the ground, scalar is more appropriate. Okay, so kind of the challenge here is to decide what is being asked of me. Is a vector question or a vector quantity being asked of me, or is a scalar quantity being asked of me? Which is more appropriate? Okay, so our scalar quantities are, okay, speed. Okay, so if we're just making kind of a list here. Whoa, I went red on red. Which column does time go in? This is another one of those ones that the societal norm is going to screw you up probably. It can't go in both. Quantity is either scalar or vector, but never both. It's scalar. As far as we can experience, time only goes one direction. Okay, unless you know something I don't. You got a time machine at home. Hey, good on you. Can I borrow it? Okay. But okay, in our experience, time is linear. That means it only goes forwards. Okay, so it isn't a vector quantity, even though sometimes we treat it like it. If I ask you how far is it to Edmonton, you go, it's like 4 hours north of here. So you've just suddenly made time a vector quantity by telling me what direction it goes. Time doesn't go north. Okay, you might go north, but time just goes. Okay, time is scalar. Okay. Now, some of the other quantities we're going to deal with, like acceleration. Acceleration is vector. Okay, work and energy are scalar. Okay, but for today we'll just deal with these ones here. Okay, so our vector quantities are going to be displacement and velocity, scalar, distance, speed, and time. Okay, questions so far, guys? Okay, so this is just definitions. Okay, you don't need to copy these down there in your notes. Okay, scalar quantities are any measured quantity that has only a value or only a magnitude, so 40 kilometers. Okay, 75 kilograms. Okay, mass is another scalar quantity. Okay, so if someone asks you what your mass is how much of you there is. That doesn't have a direction. Your weight, on the other hand, is vector. Another one to mess with your mind a little bit. Okay, it's another one. What's that? Your weight can change, and not because you actually change your mass, because your mass can also change. Okay, if you work out and put on muscle, your mass will change. Okay, but your weight can change just based on where you are. Okay, if I'm standing at the equator at sea level, I will weigh less than I weigh here. Okay. The reason is I'm further from the center of the earth there, so I actually weigh less than I do here, or I'm actually closer to the center of the earth. Because the earth is not perfectly round. It's still round. Okay? Because all that flat earth crap is crazy. Okay? The earth is round. And by the way, if you believe in flat earth, you will hate everything I say in this whole course. You might want to drop today. Because that's crazy talk. Okay? The earth is round, but it's not perfectly round. And so as a result, in different places on the earth, you're actually closer to the center, which makes you weigh more, even though your mass is exactly the same number.
Is it a radical difference in weight, or is it only?
No, we're talking like, you would feel maybe 1 Newton worth of force different if you were standing at the pole versus at the equator. Yeah, it's not, I mean, the earth is like if I took a basketball and I just pushed the two ends a little bit. It wouldn't be perfectly round, but it wouldn't be an egg, or a football. It would just be slightly flattened at the top and bottom. Okay, so scalar quantities, anything that, so kilometers or hours or kilograms, okay, things like that are all going to be scalar quantities. Okay, distance is a scalar quantity that measures how far an object has traveled. Doesn't care which way, just how far did you have to go. I mean, if I walk back and forth across this classroom 100 times, okay, I'll probably walk close to a kilometer. Okay, but if I end up back here where I started, what would my displacement be? 0. So I would have walked a distance of a kilometer, but didn't accomplish anything because I'm right back here. Okay. Speed, scalar quantity that measures how far an object travels in a set time interval, 100 kilometers per hour. Okay. 10 meters per second, whatever we choose to measure. Okay, vector quantities are any measured quantity that has both magnitude or value and direction. So 40 kilometers forward, 3.2 kilometers at 18 degrees west of south, 750 newtons down. Okay, things like that. So things can be vector if they have both a measured value as well as a direction. Okay. So your weight, incidentally, would be in newtons down. Okay. Incidentally, that's a fun game to play anytime someone asks you how much you weigh. Okay, because it's a rude question to ask. Right? So if someone ever asks you, do this calculation. Take your mass, which is what you would normally call your weight, okay, in kilograms, and multiply it by 9.81. That'll be your weight in newtons. Tell them that and watch their reaction. It's fun. Okay, somebody asks me how much I weigh, and I tell them 780 newtons. And they go, and then they find someone else to talk to. Just like totally cool. Okay, but it works. And I don't have to lie either, because that is my weight. But it's completely meaningless to most people. They have no idea what that actually means in terms of what my mass is, which is what they really wanted to know, which is none of their business. Makes it fun. All right, velocity, vector quantity that measures, okay, how far and in what direction an object has traveled from, the rate at which it changes its position, so during a set time interval. Okay, and then our formulas are these ones here. Speed is distance over time, v equals d over t. Velocity is displacement over time, v with the arrow equals d with the arrow over t. You don't need to write those down because they'll be on the formula sheet that you get from me shortly. Okay? All right, is that all familiar? That's basically exactly the way I taught it in Science 10. So if you have a Science 10 class, hopefully that seemed really repetitive. Okay? All right. Okay, so let's look at kind of a simple example here. So let's say we have a person who is standing 1.5 meters to the right of this Inukshuk, and then they move so that they are 3.5 meters to the left of the Inukshuk. Okay, I want to determine their displacement. Last year in Science 10, we learned that displacement is calculated by taking your final position and subtracting your initial position. Okay, now just looking at that, what do you suppose their displacement is? Like, we could almost do this kind of commonsensically. How far do they go? They start 1.5 meters on the right and they end up 3.5 meters on the left. How far do they go? 5 meters left. That would be their displacement, right? They go 1.5 plus 3.5 is 5 meters to the left. Okay, that would be like the common sense kind of way to look at that. Okay, that would be their displacement, 5 meters to the left. What would their distance be? Five meters. That's how far they walked. Because they didn't change direction, okay, they just walked in one straight line, their distance and their displacement are equal. Okay? They're only going to be different if you change direction. Right? Now, if we do this algebraically, which is what the question asks us to do, my final position is 3.5 meters left. Okay? My initial position is 1.5 right. How do I represent left and right algebraically? They're opposites, so one would be positive and one would be negative. Okay, so I would say my final position is negative 3.5 meters minus positive 1.5 meters. Well, if I do that, 3.5 minus 1.5 is going to give me negative 5.0 meters, which is 5.0 meters left, because I made left negative in that question. Okay, is that ringing a bell? You would have done something like that in Science 10. Okay. Probably with graphing. We've been more to with graphing. Okay, I would like you guys to try those 3 questions. See how we do on those. Okay. Give you a few minutes on that, and then we'll go through them together. All right, so on number 1, okay, we got these sprinting drills that include running 40 meters north, walking 20 meters north, then sprinting 100 meters north. Do we go north in all of those? So if we do, can we just add those numbers together to get the total displacement? Is the total distance going to be the same number? Just minus the north, without the north. Okay, so our total displacement, 160 meters north. Okay, because we go 100, or sorry, we go 40, then we go 20, then we go 100, so 160 meters north. Okay, if we were talking just the distance, it would just be 160 meters. All right, how many people have done number 2? Okay, so on number 2, okay, we got a basketball player that's doing a give and go, so they fake one direction, so they move 0.75 meters to the right, and then they move 3.5 meters to the left. What's the player's displacement from the starting position? So being able to identify our initial position is important. Okay, I'm just going to draw a dot here where that initial position is. Right? The person does 2 things. They move 0.75 meters to the right, and then they go 3.5 meters to the left after that. Okay? Their total displacement is how far they end up and in what direction from where they started. Okay? So if I'm doing that and looking at this mathematically, okay, I would have basically like 0.75, okay, plus negative 3.5. Okay? Those would be the two parts of my trip. Agreed? Okay. And so what that's going to tell me is that I'm going to end up 2.75 meters to the left, because it'll end up being negative 2.75. Okay. Now, notice how I drew that. Okay. This is kind of the start of the principles of vector addition. I drew two arrows, each arrow representing a section of the trip. Those arrows, their length represented their magnitude. So the 0.75 was significantly shorter than the 3.5. Okay? And they pointed in the direction they told me they go. One went right, one went left. Okay? And I drew them like I was telling a story. First I drew the 0.75, and then from the end of that, I drew the other one because it happened after the first one. Okay? We call that drawing them tail to head. Okay? All vectors are drawn tail to head like that. Okay? All right, questions on 1 and 2? Okay. Now, number 3 asks you to do both a scalar and a vector calculation here. Okay? So the person's doing like bricklaying, so they're putting the mortar, which is like the cement, the gray cement stuff that goes in between the bricks. So they're just smearing that on with a trowel. Okay? While they're doing that, their hand goes back and forth, so out and back, a distance of 1.7 meters 4 times. So if they go out and back 4 times, where do they end up? Back where they started. What's their displacement? 0. But their total distance is 1.7 times 4. Okay, because it said went out and back a distance of 1.7. That means out and back is 1.7 meters total distance. Okay, so if I take that and I multiply it by 4, okay, I will get 6.80 meters as my total distance, but a displacement of 0 because I ended up back where I started and my position did not change. Okay. All right, everybody all right with that? Okay, we're going to leave it there for today. Okay, for nighttime today, you are to stay here. Okay, for the first week, I think, or so, or 2 weeks, I can't remember what they said, but for the first little while, you're supposed to stay in your period 3 class until you have enough work to, I guess, reason you going elsewhere. Okay? I just deliver, don't shoot the messenger. Okay?